everybody, and welcome to the lecture today. Today, April 14th, 2020. How's the stream? Because I don't have it open. I hope it's a little bit iffy. I'm looking at the colors here, but I think the internet is somewhat stable. So, without further ado, actually, let me turn the light on. I forgot to turn on. There we go. I think that's much better. Okay. So let me go ahead and pop this open. Say in the chat, how are we doing on the video? Are we good on that? It looks good. How many viewers do we have? Because I don't have it open, so you can't see. I'm trying to be as lean and mean as possible with internet usage to just focus it just on this. 28. Okay. All right. That's pretty low, but hopefully they show up. So, all right. Well, so we have a couple of things we're going to do today. We're going to spend about the first half of the lecture talking about graphs. And then from there, we're going to jump into the review mode. And so the test is done now. As we speak, the TAs are taking the test. And so we will get the feedback from them, or I will get the feedback from them. And it should be good, but it's a rather short test. It's only, I think, 20 questions. I did create a review thing, and we'll talk about it. So anyways, I want to talk about the test right now. I want to get this done so that we can switch into test mode. So let's jump right in. I hope you all turn in your hashing assignment. That was due yesterday, I think, or last night, or Sunday night, one of those days. So, okay. A, B, C, D, E, of course. Yeah, I mean, it's easy. So anyways, okay. So last time, by the way, I guess this is some logistics. So this recording will go on YouTube and it'll also go on Twitch, but the Thursday one will not go on, because that'll be strictly review. That will not go on YouTube recording, but you can see the video on Twitch if you want to rewatch it. That's because there's no point in putting on YouTube the lecture. That's just Q&A. So anyways, but this one will go on because I'm talking about class material. Okay, so last time we talked about adjacency matrices, and we can jump in 36 years. Okay, it's going up. We can kind of very, very quickly review that. And then I want to jump into adjacency list. And I want to talk about all those three algorithms on just a introductory level. And then on Tuesday next week, we will get deep into how to actually code them, even though you won't have to code them for a homework assignment. Well, you might code the depth first search indirectly in another assignment, but you won't have to just do an assignment where you're coding any of these algorithms. But you will definitely have them on the tests, on the final, that is, where you may have to code them. I don't know. We'll see. Okay. So, all right. Well, we know that a graph is made up of vertices and edges, and the edges are the ones that connect the vertices. And if those edges are in one unidirectional, so they can only go in one direction, we call that a directed graph. If within a directed graph, we have a way of coming back to the same spot that we started from, so like that, then we call that a cycle. So this will be a cyclic graph. If we don't have something like that, this is now an acyclic graph. But both of these are directed. The undirected versions of graphs are always cyclic because you can go back and forth between any edge. So there's no point in considering acyclic versus cyclic graphs. And yes, you should get flash tracks from the Inception assignment. Except back then when I said that for search, now it's like you're actually doing the real stuff. So it'll be really cool to jump in and actually show you that. And you'll see that after you see me, not necessarily today, but next class, when you actually see me go through the actual logical algorithm to get the first search done, you will see like, oh man, I wish I'd known that for the assignment. So yes, you should get PTSD from that. So anyways, so I think that's a really quick review on graphs. And like I said, either of these graphs, we are just assuming they're all the same weight, so we don't put them. But if we want to say that a certain edge takes longer to traverse than other edges, we can add weights by putting numbers next to them. And so now we're saying this edge here takes us half the time that this one takes us. And so that introduces a whole new concept of it is not just about being able to get from a node to another node, but how fast you can get there. So if you want like a representation of what my internet looks like, you know, here's my house and here's a couple of other houses, and there's a little box here, and they all have a single edge coming in, and it's a directed graph, because the way Cox works is, I believe they have a bunch of cables. Each of them can do each channel can do 36 megabits per second, and so they have a bunch of downstream channels, and then they have like one upstream channel that can do 36 megabits per second. And so from there, they run a line to the main box, which is connected to a bunch of other little small boxes. And then from there, it goes to the main central. And so this is the last, what they call the last mile. And so, for example, my internet is really bad because both these lines and these box are overloaded. So really, this channel is okay, which is why I can send the videos right now. But these guys, I'm not even getting a channel. Look, I'm getting 2 megabits per second. So that's like literally 136 divided by 2. It's early in the morning. It's 16. No, 32. That's 17, 18. Early in the morning, it is noon. But early in the morning for me. But anyways, yeah, so that's a cool representation of her graph. And of course, what we need to do to improve this is to separate these into multiple nodes. So these come up with a cable and these come with a cable because they have multiple cables here, or better yet, a better communication here, because clearly this is being overloaded, but you know, Cox doesn't listen. So anyway, so there's my representation of why the internet sucks. So, okay. So how do we represent this other than pictures? That's when we want to talk about adjacency matrices and adjacency list. And that's a way of taking a picture and converting it into something we can feed into a computer, which can then create the tree or the graph. You know, with the tree, we have the traversals, which we then use those to build back the tree with pointers and everything. But we needed to give it something. Or in assignment 6, I think it was, you had the level order traversal with the little flags to indicate the wildcards to indicate empty spots in the complete tree, or to make it a complete tree, and then you could do that. But you have to have some sort of numerical representation. So we said that the way to do that with a graph is with adjacency list or adjacency matrix. And so we talked about adjacency matrix, but I wanted to do another quick example of that. And so if you remember the math representation, let's go ahead and make a little graph here. We'll make it rather simple. And this time it will be would you want directed or undirected graph? We'll do an undirected graph, and then we can do a directed one afterwards. But anyways, let's do this undirected one. And we have to name the nodes. So let's just use letters for those. A, B, C, and D. And maybe to make it more interesting, we can do that. Yeah, okay. And so if we represent this mathematically, if you remember the notation from last time, is we have our graph is made up of vertices and edges. And these vertices are made up of A, B, C, and D. And the edges, because it's an undirected graph, we use parentheses, are made up of A to B, A to C, B to C, and B to D. And I should have the number of lines here should be the number of things I have here. Notice that I could have, and then we put this in these brackets. Notice that I could have also written this like this. P to A, and then literally everything else the same. I can have a lot of combinations here. Because it's undirected, it doesn't matter which of the two vertices comes first. It just means that there's a connection between A and B. So you could say A and B or B and A. You could also say A and C or C and A. So how many combinations you could have? That's a 251 problem with combinatorics. So yeah, #triple bar, yeah. Ooh, I'm getting a red line on the internet, so it might be lagging a little bit. Ooh, it's really low. Okay, it's getting better. Okay, it's green now. Okay, so we may have had a little bit of a lag. So, anyways, this is all cool, and you'll see that that an adjacency list looks a lot like this, but we're gonna do a matrix first. Yeah, I can see the bit rate is really struggling to, like, it's literally right now it's 180 kilobits per second, and so I'm not surprised that it's dying because of that. No, it's 120. No, it's 599, so it's going up a little bit. Yes. Hashtag Cox. Okay, so I'll just give it a second while I drink some water. It's just redlining all over the place. If it continues to lag, I'll try to take your other stuff out of the Wi-Fi. Look, man, I'm wired connection right now, and I have literally no other device on Wi-Fi. In fact, to avoid any potential issues like the other day, I literally turn off the Wi-Fi so that nobody else can use the Wi-Fi in the meantime. So I have literally the only connection in the house that is actually connected to Cox. Cox Rona. I like that. Hashtag Cox Rona. Okay. All right. So we'll just keep going, and then tell me in the chat if it gets way too laggy, and then we'll try lowering the bit rate. On your end, remember you can turn low latency off as well. Yes. And worst case scenario there is a YouTube video, but I'd rather, watching it live is better for the most part, because you can ask questions and things like that. Otherwise, then you can just pray and hope that people ask what you're questioning. Okay, so we're green now. We're at 26.8. That's as good as we can get. That's a good number for me, because I set it right now at 2,500 for the upload. So, okay. All right, so the way that we're going to represent this with an adjacency matrix is a two-dimensional array where we can have sort of the from and the to. And so we have A, B, we put all our nodes, A, B, C, D, I think it's just up to D. And then we have to put them on both sides. And there's our 2D array. And of course, in the 2D array, you had to number them. So you can just say this is like 0, 1. You can use an enum if you feel like it, I guess, if you really want to call it A, B, C, and D. But you number them. And so that numbering represents, if you have an array called R0, let's say 0 represents this spot. And then R, let's say 1, 2 represents 1, 2 is representing this spot right here. Okay, of course you can flip it. You could make it represent 1 and 2 this way. That's an implementation choice, but remember in C++ it's a I put myself in the dark spot here. I believe it's a row major language, but there's a difference between row major and column major. That's like a CS135 question. What it means is that this is usually the column, and this is usually the row. And I believe, chat, help me out. Which one of those it is? Hit it on Google, and you'll be at it in 5 seconds. I'll refresh that when I teach 135 in the summer session too. But that's what it really means. Some languages, like I believe, like Fortran, have those flipped around, which is really weird. Maybe it's column major because column comes in first. So, I don't know. Chat is not saying anything. Let's see. Is C++ row major or column major? Row major. So, row major. Okay. Yay. All right. Worksheets will whether worksheets or not are graded by the test is up to the TAs. And if not, then we can go over it on Thursday. So, okay. All right, so now that we have our little 2D array, we just gotta insert all of these. So first of all, we can just make a diagonal line. I want to say horizontal for some reason. Diagonal line between every single node, because each node goes to itself. Interesting. Okay. Garbage posting. Yeah, I'm not surprised coming from the anime people. But okay. All right. So anyways. So now we can go ahead and list the scenes. So let's go ahead and, since we're saying from, we're gonna pick all these spots and put them in. So from A to B means from A. So here I'll highlight it so you see what I'm looking at. From A to B. From A to B. So that's right there. Next one. From A. So I guess we can just use red for all of them. So here we got another from A and then to B. Or to C in this case. So from A to C. So that's right there. And then you do the rest like that. So from B to C is going to be right here. And then from B to D is going to be right there. And then you're done. And because this is not a directed graph, and because it's undirected or unordered is another word for directed. So remember, directed is ordered. And undirected is unordered. And so because of that, we would consider this an unordered graph. And because it's unordered, then you only really need 1/2 of the array, because the other side is like mirrored. So they're not my people. That would be essentially if we do like B to A, which would be right here, C to A, well, B to A, C to A, which would be right here, and then C to B, which is right here, and then D to B, which is right here. And the only reason that I did them by hand is because I have a hard time seeing the mirror, but the mirror is there. The mirror is like that. It's a really crappy line. But yeah, you can see that it looks like a mirror. So like it's symmetric. That's what it means. Okay. So if we were to do the same thing, but it was a weighted graph, then it would still be a mirrored. It's just that the numbers, and that's actually a lot easier to mirror. Visually, it's a lot easy to see that. So for example, let's go ahead and do a directed version that is also weighted. How about, or no, because you won't see the mirror. So here, let's just do this mirrored with weight. So let's say 1, 2, 5, and 1. Okay. So then B to A, that's a 1. A to C, that's a 2. B to C is a 5, and B to D is a 1. So then in this case, how is this going to change? This is such a pretty picture that I don't want to erase it. So I'm going to make another one. Okay, so and now we can go ahead and kill it. Okay, and then let me bring that picture down. You can do it directly from here. You don't have to do the math thing. Although I do want to see this math stuff in the test. Math stuff. So anyways. Okay, so from A to B, that is going to be right here. A to C is a 2. B to C is a 5. And B to D is a 1. And I think that's it. 2, 4. Yep. And so here is a lot easier to see the mirror. So like here this 1 mirrors, and here this 1 mirrors, and here there's 5 mirrors, and here there's 2 mirrors, and we should get, yeah, the same thing. So that's what it would look like with a weighted undirected graph. Okay. Next, we're gonna do a directed one. Shall we do it's the same graph directed? I think that's probably for the best, just to gain some speed here, since I did talk some kind about this partially last time. Okay, so now in this one, we are gonna make it directed because in a directed graph you can still see yourself, we're still going to leave that horizontal lines of ones across. However, you'll see that it's no longer symmetric, because that's a, oh man, there's no easy way to kill the red line. There's no easy way to kill reds. There we go. Okay. This bothers me. There, looks pretty. Okay, so for the directed one, we're gonna start with a, let's just jump right in and do one that's weighted. Otherwise, it would just be ones instead. And when I say ones, that means that when you're actually programming it, you can make them booleans and then set true if there's a connection, or zeros. So in other words, you could fill the rest of this graph with zeros if you want. Usually I don't do that, and usually you don't see people do that because it's just redundant and annoying. So if you see blanks, you can just assume then to be no connection, which if it's booleans means a zero, or if it's on a weighted version, you don't want to put zero because that means it's an instant edge. It's like you get there before at the same time you start. You definitely don't want to have negative edges because that's time traveling. There are algorithms, however, that can handle them, and you will learn that analysis of algorithms. They're really cool, and I wish we had to talk about some of those, because that would introduce some really cool assignments, like time travel assignments. So if I ever teach analysis of algorithms, that's going to be my assignment for the negative edge shortest path problem. It's going to be like Back to the Future style. But anyways, you know, a man can dream. Okay, so that's why you see me leave them as blank. But in a test or something, you can leave them blank. Or if it's a unweighted version, you can set it to 0. If it's weighted, then set it to -1. Okay, so I'll do that for the weighted one, just so you can see what I'm talking about. So you fill these in with -1s. And then for this one, you can fill them like zeros, but like I said, that one I'll leave empty. Okay? So anyways, let's go ahead and do this. Negative edges. Yeah, there is such a thing as a negative edge. Like that. And that if we have a negative edge in an undirected graph, that means that the shortest path to any node is negative infinity. Because you can keep going back in time to get there earlier until like before time even starts. That's not very cool. But some graphs, suppose you have the following graph, and it's directed, and you have a negative edge here, and then you have positive edges here. It might be faster to get, say you're trying to get to this node, you know. Well, here, let me just actually put numbers in. So let's say this is a 5, and this is a 1, and then here's a 3, and then maybe here is a 1. Okay, and maybe, actually let's make this a -10, so make this more obvious. So now if I tell you, and then maybe like that, okay? Or 2. So now if I tell you what is the shortest path from this node to there, you know, one way is to go this way, which is 2, 1, and 3. That's a length of 6. I can also go 2, 5, -10, and then 3. That's 2 plus 5 minus 10 plus 3. 2 plus 5 is 7, minus 10 is -3. Plus 3 is 0, so we actually get here at the same time that we started, and that's because we basically time traveled back. That's what the negative edges do, and that's actually useful in some problems. And so there are algorithms to compute this to take it into account. That's the shortest path, the way that I'm going to show it to you, cannot handle negative edges. It just assumes that cannot exist. So it's a really cool template for making time travel assignments, I think. Just a cool thing to do, you know. But anyways, okay, back to this. And the reason I'm showing you this is because I do think it's useful for you to be aware at this level, at least, that there is such a thing as negative edges, whether or not we use them. Oh, my dog is here. Oh, Padme. So okay, so anyways, go back there. There, she goes behind me. Okay. So now we are going to make this a directed version of this graph, and we'll make it a weighted directed graph. So we'll keep the same, how about we keep the same weights, but in this case, we're going to put some arrows. So we'll make that one go this way, we'll make that one go this way, maybe that way and that way. And so question to you, chat, is this a cyclic graph or is it a directed acyclic graph? You tell me that. Okay? And then in the meantime, I'm gonna do this, but I want chat to respond whether there's a cycle there or not. So while chat, okay, so we got the response already. Oh, nice, there's not that big of a delay. So it is indeed a cyclic graph because there are no cycles. It might seem like there's a cycle here because you're like, oh, it's going back. But the case is that it is not a cycle because while you are turning back, you don't actually come back to A. There's no way from any of these nodes to come back to the same node again. So that's basically all there's to that. So, okay, let's go ahead and throw them in. So from A to C, that is going to be 2. So now it actually matters where the from and to are going. So since we know this is a from side, then this A to C has to go here. It cannot go here because that would say that it's going from C to A, which is not the case here. It's only going to C. It's only going that way. It's not going backwards. So that goes there. Furthermore, we have from C to B. So that's from C to B. So that's a 5 here. So that's this edge right here that we're working with. So here I can try to color code them a little bit for you. So that edge is this edge here. And then this edge is this edge. And then let's go ahead and do this edge here from B to D. So that's from B to D, that's a 1. And then we didn't add a weight to that last one. So I was hoping chat would tell me a weight for that, but I'll just throw in myself. So let's just go ahead and do another 1 just to be a little bit confusing, but I'll color code it for you. So that's from A to B. That is going to go right there. Okay. And so you can see now that it's no longer symmetric. And so the thing that somebody quite correctly brought up last time is that this wastes a lot of space, right? Or it can. It doesn't necessarily have to, but it can. What is the space complexity of this algorithm? Oh, not this algorithm, but this representation of this. Oh, why is there the diagonal version of 1s? Because we like to represent the fact that you can go to yourself with a 1 across, and that takes you 1, which is the smallest time. You could also put it to 0 if you would like in a weighted graph like this. But then you gotta make sure you consider stuff that it's not present with -1s, okay? So that's usually what we like to represent. So yes, you are very correct in terms of the takes n squared, although here we don't like to call it n squared. We like to call it b squared, and b standing for the vertices, right? Or set of vertices. So in this case, 4 of them, so this is 4 squared, 16. And there are indeed 16 spots here. But you can see that we're only really using about 5 of these, right? We have 1, 2, 3, 4 actually, because the diagonals is a given. If you want to throw those in as well, then sure, it'd be 8. But all the -1s are really wasted. We don't need them. So this is inefficient in terms of space if we have what's known as a sparse graph. A sparse graph is usually, if it's a directed graph, is usually a weakly connected graph versus a strongly connected graph. Remember what that is? Strongly connected means that you can go from any vertices to any other vertices directly without having to follow a path. Remember, path, that means a multiple vertex route. But if you have a direct connection from each, think of them like airports. If you have a direct connection from LA to every single airport in the entire country, and every other airport has a connection to every other airport in the entire country, and by that means there's a direct flight, that will be a strongly connected graph. What ends up being the case with actual implementation of an airport infrastructure, airlines and everything, is a weakly connected graph. A weakly connected graph is a graph where you can reach every other node, but not necessarily directly. So like, you may not necessarily have a non-stop flight, but you probably have a layover and a connecting flight, so you visit multiple nodes. So that means that you can get to the other nodes, but you just can't get there necessarily directly, right? And so the little exception to that is that the definition of weakly connected graph says that in a undirected graph, it would be a connected graph, which again is saying that there's a connection, not necessarily directly. Okay, so rewatch that end of that lecture for that. So, but anyways, this will be if it's a sparse graph, it means that there's there's not that many edges in the graph, and so I would consider this to be a sparse graph. It's debatable what the actual threshold for that is, like how many, like if you think of it as a percentage, and we said like, okay, you know, how many edges could be coming out of this? This is actually a kind of a good test question. For these to be a strongly connected graph, how many edges have to come out of each node? Or in other words, what does the degree of each node have to be? What would it have to be a strongly connected graph? Tick tock, tick tock. I'll tell you the answer. It would have to be the n number of nodes. Right, there you go, n minus 1. Perfect, yes. So, because if we're trying to make this connected, I'll put that in a different color. I would have to have an edge going here, going here, going here. We have those two out of 3 of those, but we also have one here, and then one here. And then we have to do the same thing for the other one. So from this one, this one, this one, this one, this one. Those are different colors. This one, and then this one, and so on, right? Degree is just another nickname for how many edges are coming out of a node. So like a binary tree is a degree of 2. A ternary tree is a degree of 3. A graph can be any degree, and we pick the node with the highest number of edges coming out, and we say that's the degree of the graph. And yes, the easy way is amount of lines coming out of each node. Yep. So anyways, so that there you go. I'm glad you guys figured that out. So yes, if we had to make this a strongly connected graph, we would need it to be a strongly we would have to have, in this case, it would be 1, 2, 3, 4, 5 coming out of each one, and we have 5 of them, or sorry, we have 6 of them. 1, 2, 3, 4, 5, 6. So that would be 30 edges total. So that's a lot of edges coming out. You know, it's a very edgy graph. So a sparse graph would be one where there's far less amount of that, which is what we have here basically, which is we have 2, 4, 6, 7 edges on this graph here. I would consider that a sparse graph. Again, the threshold is not very clear. If you go on the internet, some people say about 15%. If we take a percentage of like this, what would 50% be? That would be 4.5 edges. However, this has 1, 2, 3, 4, 5, 6, 7 edges. So that's over 15%. That's more like 22%. I'd still consider it sparse. So I'm not going to ask you to test what is the percentage. I just want you to understand. The sparse graph is one that just doesn't look as connected. Okay? So it's a little bit of an ambiguous term. I'm actually curious what the book says on that, but I haven't opened the book, so yeah. So if it's not strongly connected to sparse, not necessarily, because if I had a graph that was like literally it had 29 out of 30 edges, you know, it has just one edge that was not connected, technically not a strongly connected graph, I would still consider that the opposite of this, which I actually didn't tell you what it's called. It's called a dense graph. I would consider that a dense graph. You know, it's tricky. I would say maybe like if we want to hear percentages, I'd say anywhere from like 40 to 50% is about the limit of what I would say is a sparse graph. Probably more like 30%. Definitely anything over 60%, I would definitely call around here. So there's your little. So I'd say the way to look at it with percentages are, for sure, 30% or less will fit here, 60% or more will fit here. This is and anywhere from 30 to 60 is going to be that ambiguous area of whether it is sparse or not. You know, it's just a term. Can you define strongly connected again? So strongly connected is if you have a graph and you can reach every node from every other node like this, even as long as there's a path to them, then we would consider this a connected graph in the undirected version. But now if this is really a directed graph, then this, even though this is not strongly connected, as you can see, we would consider this a weakly connected graph, because if converted into the undirected version, it's considered a connected graph. That's the official meaning of that. Okay? So does that make sense? Yeah, you can just convert it into an undirected graph, and then as long as there's a path to every node from every other node, I believe that's the formal definition. As long as there's a path from every node to every other node, then you're good. Why do you need it to be n-1? Because that's when it's a strongly connected graph. When it is a strongly connected graph, which only works for a directed graph, is when every node can reach every other node. Okay? So anyways, moving on to adjacency list. So let's go ahead and do adjacency list for the same graph. Question mark. I did answer, because you need to be able to reach. You can definitely have that in less than n-1 edges. You could, but I'm just saying you may have to need n-1 edges. How does connectivity relate to sparse dense? Like, is a weakly connected the same as sparse? Sparse and dense are strictly based on the number of edges your graph has, whether or not it's connected or not. But usually it seems to be the association that weakly connected graph are typically sparse, strongly connected graph are typically dense. That's just an association. But again, it's strictly based on the number of edges it has when there's something is sparse or dense. And yes, the maximum number of edges. There you go. Thank you. Okay, so now we got our graph again. And in this case, we're going to go back to the undirected version. And now I'm going to show you the other way of representing this graph. And that is using an adjacency list. Okay, so an adjacency list. Yes, good math. All right. So an adjacency list is actually closer to the mathematical representation of this than an adjacency matrix. And again, the big downside of adjacency matrix is this OB squared for space. However, the plus side to this is that you can quickly access whether an edge is connected. If I just ask you flat out, is D connected to A? Like, is there an actual edge coming out of that? That's a better question. Is there an edge from D to A? I can very quickly say D, A, and in O of one time, in constant time, I can tell you like there's a -1 there, so that's a no. There is no edge there. Okay, so that's the one plus side to this. It's very, very fast to access. It takes a lot of space, but it's very fast to access. If you need to create an edge, delete an edge, do anything to an edge, you can just get it in all of one time and then modify it. If you need to add another node to the graph, then you can just make another column here. These don't have to be in any special order, actually. As you can see here, I picked the letters in any way. So let's say we add an E to this, and E is connected to B. Well, there, and then say there's a weight of 2 there. Just add a column to both sides like this, a column in a row, and there you go. You have your E, and so now you can go ahead and say E is connected to B and put it here, and then fill everything, and then fill the symmetry with 0, and then fill the rest of them with -1s. Okay. So that's essentially what you would do to add a edge to this. So it's very easy. I mean, obviously easy in the sense that, okay, now you got to resize this whole thing. So, you know, that sucks. You have to resize the 2D array, but you know, if you're doing things dynamically, you can do that rather easy and quickly. So it's not too bad. But the point is that once you do finish resizing or whatever, again, you're still in that O of 1 time. Okay, so now adjacency list is going to be kind of another way of doing this. It has some benefits and some drawbacks. The first benefit is going to be that it's a lot easier to actually write down. There's a lot less written, and that's going to help us with a sparse graph. So, okay, the way the adjacency list works is it's a list, essentially. And you have the same thing like your from and your to. And here you have from A, B, C, and D. Oh, here we have a question. So is the diagonals... So is the diagonal ones for undirected graphs and zeros for directed graph? So in a directed graph, we consider the one to be connection and the zero to mean no connection, or also just like empty, I suppose. And so we like to say, it makes coding this a lot easier and working with the code. We like to say that if you're already at node A and you need to go to node A, then you're like, well, I'm already here. So symmetrically, the diagonals, you set them to 1, which means that you can. If for some reason in your algorithm, you said the only way you can go to yourself is to visit somewhere else beforehand, then you would set them to 0. But typically that's not the case, so you set 1s. With a directed graph, with a weighted graph, zeros are valid weight. It's just an instant weight, but it's technically valid. And so we don't like to set 1 to those because 1 involves that to get to yourself, you have to spend time. So 0 is not the best value for that. 1 is not the best value for that. The 0 is more correct of saying you can instantly go from yourself to yourself. Like, I'm going to go to Las Vegas, guys. Okay, I'm already here because I am already at Las Vegas. So that took me instant time. Versus putting a 1 is saying it actually takes time for me to go to the same place I'm at. So with a weighted graph, it's useful to have zeros. With a directed graph, you can still maintain... did I not do an example like that? I guess I could do one really fast. With a directed graph that is unweighted, you can still use zeros and 1s and not have to put... and not have to set the diagonals to zeros. So here, I guess I'll do that really fast. I thought I could skip that, but I guess otherwise I might miss some points. So we'll just throw it in down here. So let me just do this one more time, but the unweighted version, but directed. So this is unweighted and directed. Unweighted directed graph, a cyclic graph. So in this case, because it's unweighted, we can say that you can go to yourself, you can put 1s in there, and then for the other connections that you have, we'll put 1s as well. So from A to C, and from A to B, and then from C to B, and then from B to D. And that's it. Everything else stays empty, which you can manually put in zeros if you wanted, which I guess I'll put them in for this one. But you could actually put any number. It doesn't have to be 0. So if you really want to stick with the -1s, you could. So 1 indicates connection, and the weighted while 0 indicates cost. Yes. That's good. Yes. 0, no connection, 1 connection in unweighted graphs. In weighted graphs, because it's weighted, -1 means no connection. Usually. Actually, I'll say something else about that. -1 typically means no connection. 0 means a connection, but it's instant, which usually reserved for going to yourself. And then the value from there up is time. Now, why do I say I should say something else about that? Because when you do have to represent negative edges, like you actually have a real negative edge, and you're trying to implement this, what you really want to set the weights to in a weighted graph like this is to infinity. So all these -1s, when you're actually implementing this, if you suspect that if you don't have any negative edges, then you can hard code an if statement saying if negative, it means no edge. But if you suspect that there may be negative edges in your graph and you're using like a Bellman-Ford or one of the algorithms that actually can handle negative edges, then the best thing that you can do to represent these is a special value which can represent infinity, basically, because that means it's such a huge weight that you will never pick it as the fastest path because it's infinite. And so I've seen people actually represent it using the words INF. How do you code that? Just pick a really big value that doesn't overflow an integer and then make that a little defined called INF, so like there's a shortcut called something like maxin, which will give you the biggest int. But if not, then just pick something like 2 billion or something. Make sure you don't overflow. Overflow is like 2.4 billion or something. 2.6 billion, I can't remember. Just pick a really big value there. And then just hard code that as your infinity. Oh, there you go. Yeah, you could always use hex. Make life easy. Lots of F's in the chat. I don't know if I put the right number of F's. 2, 4, 6. I think it's 8. Can't remember. Let's just put like 7. Halfway down. Okay. So anyways, back to the adjacency list. Adjacency list. It's a little table, and on the left side you have your from, and on the right side you have your to. And for each of these, you're just gonna put the set of the connections. So where does A go to? Let me bring this down a little bit so I can see it better. And right now, let's go ahead and just go back to the undirected, unweighted graph, which is a simple, easy mode. And so from there, we're saying A goes to C and B. So we can just list C and B here. If you want to be OCD, you can alphabetize them. What about B? Well, B goes to A and C, so we can list A and C there. What about C? C goes to both B and A. What about D? Oh, I guess we forgot one for B. We forgot D. Nobody caught it on the chat either. Shake my head. You're watching too much anime during the chat. Ayaya, or whatever your name is. Asterisk. So D goes to B. Okay? And bam. Yeah, there you go. You're done at that point. So at that point, you're done. And look, you're like, oh man, that's so much easier than doing all of that. And I'll tell you this much. It uses less space, but it's not necessarily easier, because how do you actually represent this in a file? Well, you could have just literally put line and then connection. So like A space BC and then B space ACD and so on. And then there's one that was empty. So like suppose that E was not connected to anybody, that we had an E here that was not connected, then E would just be an empty line. And so on. So this is an adjacency list, and it's very similar to what this is like. And so if we go ahead and look at how long the space complexity of this, then I believe it's V plus E, but I will triple check. Actually, I have it written up here. Yeah, B plus E. Like that. If it's a directed graph, you do even less of these because you don't have to put them twice, right? So let's go ahead and do that. That guy's just randomly in the middle there now. Okay, it's okay. I can live with that. What's this? Well, I guess this is where we're going to put the title of this. This is now going to be adjacency list for a directed graph. Okay. We can leave that E in there, actually. Why not? We won't even give it an edge. It's not an edgy graph at this point. Edgy is just a joke. Please don't think that's actually a term. Okay, let's throw in some weights. I forgot what we had before, so we're just gonna pick a random weights. Actually, sorry, wait. We don't need weights right now. We're doing simple mode, easy mode. We'll keep it unweighted. We'll just say B is very popular. Like, with, you know, all roads lead to Rome, all roads lead to B. So we don't say it goes to itself. What do you mean? I missed that earlier. So in what context were you saying that it doesn't go to itself? Oh, I see. You're saying you're saying in this you don't have to put A on the. No, you don't, because it's assumed. Yeah. Oh, that's what that answer meant as well. Yeah, you assume that it goes to itself because it's a normal thing. This is the big brain version of this, where you keep it simple, I suppose. Okay, so from A going to C and B, you put C and B here. From B is empty because it doesn't go to anywhere. C goes only to B, and D only goes to B. We have 4 lines there. We have 4 things here. We're good. E is just forever alone. Okay, so yeah, that's pretty much all you do to do the direct version of that. You can see this is very, very tiny. And so your question should be, okay, cool. I know how to represent that in a text file. How do I represent an adjacency list in a computer? Well, it has the word list in it. And we know something with lists, which is linked list, right? So voila, we can represent it with a linked list. We can have A there going to C, V, and then we can have our B just going to null, C, V, D, V, E, null. If you want to be hardcore, you can even do something cool like this. A goes to C, and C goes to V, B goes to null, C goes to V, D goes to V, and D goes to null. And then you're in the hardcore mode. Yeah. So, because you only really need one node that represents B there. Same thing if we were using C for something else. There's no one going to D, right? Yeah. So, you don't, I mean, of course, what you don't want is if this went somewhere else. So you can't do that for every single node, but you can do that if you organize things nicely. A jagged array. You can do a what's called a rag, not jagged, a ragged array for the adjacency matrix when it's a undirected graph, because you only need 1/2 of it. So you could definitely code a ragged array to be efficient. In fact, I was thinking of making that an assignment to get you to practice ragged arrays and actually force you to only dynamically allocate half of the array. It's not that bad, actually. It's just a matter of manually allocating each row with a little for loop that decreases the size. So I'm not gonna have you do that this semester, but next semester I'll make the 3 or 2 kids next semester do that. So yeah, you get to do something far more cool. You get to do that Edge of Tomorrow continuation. So anyways, that is an adjacency list. But usually this is, so let me tell you the real world version of this stuff. Adjacency matrix is great in real world to actually store the data because it's fast. Adjacency list is good for actually loading the data into the computer because it's tiny and you don't care how long it takes to run, because it's going to go from top to bottom. It has to run every single line. So adjacency list, great for a file to actually back up your graph. Adjacency matrix is great for actually internally storing it. So when you read it from the adjacency list, you can read it into an adjacency matrix and then actually represent your graph in the computer that way without using a single pointer. The other way, the far more cooler way of doing it, is using pointers. You can represent it how you did the APL tree, which is just a bunch of pointers, and it actually makes your algorithms a lot easier. but you do lose that quick access time, because if you represent your graph with a bunch of pointers, there is no easy way to see whether there's an edge coming from one node to another one, unless you maintain pointers to all nodes manually. And then from there, you have to still dereference each of the children and see what letter they are, what identifier they are. There's no easy, simple way. Whereas with the adjacency matrix there is, because it's all of one time, and you can quickly access the two nodes and see if there's a connection there. So for the assignment, I haven't decided yet which of the two you'll do, if you'll do the pointer version or the matrix version. I do think that we'll stick to the pointer one because it's a lot more cool, but that is yet to be decided. So it's a lot easier actually, like I said, doing the algorithms with the pointer stuff. So A does not need to be directly linked to B then. For example, in that linked list, it is going through C to get to B. Well, you're still storing in a linked list, but you could do something like this if you preferred. Probably be far more efficient that way. Yeah, that's a better way of doing it. I agree. Can you list those pros and cons? Yeah, I was gonna get to that. So, all right. So now you like, in addition to the pros and cons that I said, when you would want to use an adjacency list and adjacency matrix. Okay, so adjacency matrix is always better in speed, like I said. However, if you have a sparse graph, it's much better to store the data as an adjacency list, because as you can see, it's very tiny. Like if you're doing this in the test, this is so much faster to write and draw than doing an adjacency matrix for the same thing. It's very clean, very easy, hard to make mistakes. That's because adjacency lists and sparse graphs are best homies. A dense graph, on the other hand, you could do here as an adjacency list, but you have no benefit from doing it versus an adjacency matrix, because what ends up happening is if you make an adjacency list from a dense graph, suppose that it's the highest possible graph, so that n-1 situation, at that point, this becomes more like OB squared, essentially. So for a dense one versus a sparse one. So you have, if you have a strongly connected graph that has every single edge coming to every single edge and everything, it's like complete full. At that point, you might as well use an adjacency matrix, because you're not getting any space, because you're literally gonna have, say everything is connected to everything. What would that look like? Well, that would literally look like A, B, C, D, E, A, B, C, D, E, A, B, C, D, E in every single one of these, right? So you would have 5 times 5, you have 25, which is essentially what you have here. Well, here we have 4, so we have 4 times 4, 16. But if you have that E in there, that will be 5 times 5. So does that give you a good idea about that? All right, so it's 1 p.m. So at this point, I want to switch over to test mode to start reviewing the test. I suppose, unfortunately, we will get to talk about, I guess, no, it's actually good, because we'll talk about the algorithm, and then I'll go hardcore into the how to implement it for topological breadth first search and depth first search on next time. Not on Thursday, but on Tuesday next week. Okay. But before I jump into the test, do I have any more questions on adjacency matrix and graphs, or matrices and lists? Very quick, if you want to see an example of a weighted version of this, let's just go ahead and add weights to this. So 1, 2, 5, and 1. The way you do this is you make them an ordered pair. So you can say B, comma, so D to B is 1, C to B is 5, so 5. And then for these, you need some space. So A to C is 2, and A to B is 1. Like that. And so now you associate a weight to each edge. And of course, if this is undirected, then these would all appear twice. I suppose to knock corners here, I'm going to go ahead and do that real fast. But start warming up those test questions. So kill all the arrows. Let the arrows die. It's the only way to live. Quote from movie. Okay, well, almost direct quote. So in this case, we have to put everything twice now. So I can leave all those in there. I just gotta add more. So A also now goes to I got everything with A. B under the side is gonna have 3 things in there. So it's gonna have A, 1, B, 5, or sorry, C, 5. And then D, 5. Or what happened to the weight? Did I not have a weight in there? Question mark? Oh, it's a 1. So in that case, it's a 1. And then C goes to B, and it also goes to A. I feel like I made a mistake somewhere. Nope, I think I'm good. Let's see, 1, 2, 3. I have 4 edges. I should have 8 of these. 2, 4, 6, 8. No, I'm good. I got everything. Okay, and so there you go. So that would be how a undirected adjacency list of undirected weighted graph. Notice that I'm putting the word unordered instead of undirected, even though I'm saying undirected. That's just to familiarize you with the fact that they're interchangeable. Okay, so now let's go ahead and see what we have here. Can you list the pros and cons? Is this in the test, by the way? This will not be on the test. This will be on the final. Okay, what are the time complexities for inserting, deleting, and accessing in the graph? That depends on how you're inserting. So if you're inserting into an adjacency matrix, as I said, all you gotta do is technically O of 1 time, assuming that the resize doesn't take time. If not, then it's whatever the resize takes. With an adjacency list, it just takes pretty much constant time because you can just add another node here. Again, these are not in some special order. So if I was to insert like node T and node T was connected to D, then I can just add their TD and I'm done. And if it's weighted 1, then I can do that. Of course, you know, the problem here being that now I have to add it to D as well. So you have to go and find that and also add it here. But if it's a directed graph, then I wouldn't have to do that. So either way, that takes O of 1 time. I want to erase it so people don't get confused, but it's on the video, so you can take a screenshot of the video for that. Okay. That's inserting, and same thing for deletion. With deletion, you can always delete it and just mark that as an empty column, and next time you insert something, you can just refill it in. And accessing, as I said, O of 1 time with the adjacency matrix. With the adjacency list, it's not going to be O of 1 time. It's kind of like the accessing time with hash tables with separate chaining. It's going to potentially take O of n time, and in this case being the number of vertices. Because if you have a specific vertex that is, you know, connected, or that has an edge, I suppose, has an edge to every other vertex, and you're keeping this as a sort of a linked list, that you may have to traverse the entire linked list to get to the to find out well, you don't know this, right? You don't know that it has an edge to everything, and you're seeing if it has an edge. And so you have to look at all of them and say that you're getting unlucky and it's the last one in the linked list. Then you have to check them all. So that's potentially O of n time, n being the number of vertices. So taking O of v time. And now you're asking, well, can you do what I did up here? Where you have like multiple pointers coming out? Yeah, but you got to go through each of these pointers. Yet again, if you have v of these, O of v time. On the Vigo cheat sheet, they actually don't list graph data structure. Well, that's okay because you got yourself somebody that can tell you what it can be. Yeah, the only time it's not constant is when you're dealing with adjacency lists. So you mentioned programming questions on the review page. Will there be programming questions? Yes, I will go more in detail in just a second. So the time complexity is pretty much dependent on the data structure that the graph is implemented with. Absolutely. Here's the thing. The other thing that I haven't really talked about, but I was telling you about, is once you read the data in from an outside source, like a text file that is in an adjacency matrix format or an adjacency list format, once you actually read it in, you can do two things. Usually, you don't want to actually internally keep it as an adjacency list, although you can, I suppose. Don't let your muse be dreams, if that's what we want to do. But typically, it's kept as an adjacency matrix, or as I said, as a bunch of pointers. But the moment you throw in pointers, now it's very, very hard to just even find out what is connected to what, or whether there's something exists in the graph or not, at any point in time. Like what vertices even exist in there. So all the time complexities go way down and super slow to be able to deal with a graph that's kept as pointers. Because you gotta start, assuming you have just a starting pointer that just points you to somewhere in the graph, then you got to like work your way around the graph. Or if you at least keep an array of pointers that point to each vertices, then okay, that gets you somewhere, but it's still going to be relatively slow. But it's cool, and it's more real in the sense that also you don't waste space if you do it with pointers, because all you keep are the pointers that are active. If there's no edge, then it doesn't use up space, right? So you'll get more of a feel of that when you're actually implementing it. And that is something that I was going to ask in the write-up for the assignment 11. Okay, jumping into review mode, unless more questions of this come up, let me go ahead and pop open Canvas. There's when I Googled it, whether it was C++ or a major. Okay. So I'm not going to accidentally open up the gradebook or anything. Imagine doing that in 2020. So, okay. Midterm exam. Should I click on that, chat? What do you think? I don't know. Not really feeling it. But I'll click on the review. Maybe I'll click on another tab, because then you can be like, look at that. It exists. So, okay. All right. So, midterm exam review 2. So I went ahead and created this little spreadsheet thing, and I did go ahead and fix this issue here. Thank you for pointing that out, person. And so basically, let me make this a little bigger. Okay, so the exam, as you all know and voted on, is April 17th, this Friday, from 12 to 12. So it starts at high noon and it ends right before the strike of midnight. And so, however, you don't have the 12 hours to do it. You have the 12 hours time range to do it, but you only have up to 3 hours to do it. And so what that means is if you start right at 12, then you have until 3 p.m. But if you start at 10 p.m., you technically only have 2 hours, because then it would cut you off, as some of you found out in that one quiz because you procrastinated. So, hey doc, did you know there's this cool trick you can use, Control Tab? I don't know. I know the trick that says Alt F4, click. But yeah. So anyways, so what that really means is don't start the test after 9 p.m. Otherwise, you will have less than the ideal time. However, the test can and should be completed in about an hour, which gives you 2 hours to figure out any problems that you have, whether your internet explodes, which means you have Cox, or if you have problems uploading files and things like that, you can basically work around. What you should not do is discuss the questions on Discord if you have a question about it. I know when you have a question about homework, you post it on Discord. Don't do that for the test. Send me a direct message, an email, or to the TAs. We may or may not answer. Hopefully we will. I should be awake during the test, but if not, then don't fret. Do your best, and then I'll have on record that you asked me a question as well. So, yeah. Will we be able to go back questions and tests? Yes, I added that feature. So now you should be able to go back to questions and tests, and you should be able to see the entire test on the same page as well. So, and the reason I added that is because I do ask follow-up questions to previous questions. So like, there's code, and you do some code, and like in addition to that code, so I can give you some code and I say write code to do something else in this function or in this program. And then you write that code. And then the next question asks, okay, add this other feature to this using from the original code. So it's nice to be able to see the code in the same page. So yeah. Okay. So, sorry, Corona is killing me. So there's 20 questions in the test, and there are no extra credit questions. So I may do some sort of extra credit thing to kind of, keep that extra credit idea, but it won't be able to test. I just don't want like issues that come with that, with the timing extra and whatnot. I can set up some sort of timed extra credit challenge like I've done in the past. So you can do that, or there's whatever. We'll figure that out. But I'd rather keep the test just to the test and not run into problems. So it's 4,100 point test. Again, don't panic. If you feel scared about that, you can divide all the points distribution by 100 and you get 41 point test if that makes you sleep at night. So you can do that. And then, I think most questions are like around the 100 and 150 point questions. So, the reason I do this is because I like whole numbers. So easy. Okay. The topics of the test are going to be, by the way, how many viewers do we have? Somebody update me on that. Are going to be traversals or trees in general. Concept, there's going to be a couple of questions, at least 4 or 5 questions. 31 right now. Ooh, that's pretty low. That's like a third of the class. I should check my UNLV and see how many people dropped. Maybe that's why. But it's okay. I'm assuming the 31 of you here will do much better than the ones that are not here. So the fact that you're watching this is probably a good sign. And if you're watching it on YouTube later, it's half of a good sign, but it's still half of a good sign. It's still better than nothing, So, all right. So trees. You are going to have this. So this is, if you think of the worksheet, that's a good study example. You had building a tree from traversals, and that means don't get this confused. I don't want to hear questions about this in the test because I've been saying it a lot of times, and you went through you went through this on the worksheet. I'm going to give you 2 traversals, either an in order and pre-order or an in order and post order, and I'm going to tell you these 2 traversals make a tree. So go ahead and make that tree, and you use the algorithm that I showed you in class to do that. And I can go over an example of that algorithm if you'd like, once I finish going over this. But you build one tree that has both traversals in it. So if I went ahead after I built the tree, I perform all my traversals, I would get the same traversals that I started with. It doesn't mean build 2 trees, one for each traversal. No, that's easy. I want you to use that algorithm. So, yes, you have taken my test in the past, though, Kawa. So, he's a 302 veteran. So, that's when I made up the test. The cool thing about this was that we were in the Mac lab, so you could have extra time, right? So you got, and then the class was like 5:30 p.m. So you guys were there like until like 8 p.m. or something taking the midterm. So it's good times. Yeah, that was the longest test I've ever made. From there, it's gone down. Made them shorter. So he can tell you more about the test style. So yes. what was the extra credit question that I asked? I can't remember. So anyways, you will have to do the algorithm. You will have to do all traversals in order, pre-order, post-order, level order. You will have an ABL question where you have to insert things into the ABL and you have to delete some things. And as you do, you have the rotations. So here's the big thing. For building the tree from traversal and for ABLs and for heaps, I would normally not ask you to show this much work, but because you have more time and because it is the internet and because you could literally just plug in some numbers and run, assuming you did the assignments, you could, or even on the internet, you could find something that could perform these rotations for you. I want to see your work. So I want to see each step of your rotations or your insertions or your building of the tree. Like, again, I can show you an example of the kind of level that I'd expect, but I want to see that. Okay? Otherwise, you will get a 0 for that. I want to see work. Did you ever show how to build a post-order in-order tree? Yes, post-order and in-order will work. The one that can produce more than one tree is when you have a post-order and pre-order. So if you'd like, I can do, I'm pretty sure I did, but I can do an example of post-order and in-order. It's the same thing as pre-order and in-order, except you don't start from the left to right, you start from the right to left. That's the only difference. And but the pre-order and post-order combination, that can make more than one tree. It's not a unique tree. Some cannot even make a tree at all. So, yeah. Anyways, there are heaps on there. Again, I'm asking you to heapify it, which is one algorithm. Then I'm asking you to delete stuff, which is another algorithm. And then I'm asking you to insert stuff, which it's another algorithm. There's 3 separate algorithms you're doing. I don't want you to just use the insert algorithm to heapify. That's a separate thing. Again, why am I being so pedantic about this? Is because I want to test your knowledge and understanding of the different stuff that I've taught. When we delete the root in an ABL tree, are we replacing it with the rightmost child or the leftmost child or the rightmost child or the leftmost child? That sounds like trolling, but it's actually correct. You will replace it with the in-order predecessor, which is going to be the left child of the node that you're deleting if it has no children. If it has children, then it will be the rightmost child of the left child. So I think for that, we need a picture. Otherwise, it's like a tongue twister. So the review. Oh, it's stuck. Okay. So if we have node A, and you have nodes B, well, I guess if you want to do in order, I, A, E, sorry. Okay. So if this is easy mode, all you do is you replace, if you delete E, you replace it with A. Easy mode part 2, if you have negative A, I suppose, something before A, that's okay. You still replace it with A, and this just moves up, right? So you're good. Hard mode, I suppose, if you have either 2 children or just 1 child. So you have something like B. In this case, you go to the left mode, you have the left child, and then you got to go to the rightmost thing there. So you'd replace it actually with B in that case. Other hard mode. Suppose that this was D. Here you could have, well, if you had E there, then you replace it with E, but that's no fun. So here you have C. So here you got to replace I with D. But then what do you do with C? Well, you just move it up there. Okay? So, yes. Whenever in doubt, it's always the in order predecessor, which means if you do the in order traversal, it's going to be the one before the I. So it's the left child, or if that has children, it's the rightmost grandchild or further on thing, I suppose. Will this review be posted with the lecture? I haven't even get today. Yes, this will today, but the one on Thursday will not. That would only be on Twitch, which I think you can also rewatch, but no guarantees there on quality and everything. But today's review will be for sure. I think in general, do you find the meridian so also the left or the left and the left or the right or right down? I don't know. I guess you could think of it that way, but I like to think of it just in order predecessor, because median sounds sketchy. You're not trying to balance a tree. You're just trying to replace something. Then you do the balancing. Okay, finally, hash tables. You will have a hash table questions just like you did in your worksheet. You will have a function that just like you did in your worksheet where you got to create the hash function, but it is a far easier one. At least I think it's easy. Either way, you have 3 hours. Right? No, it should be really easy. I mean, if you can't get it right, then there's just no hope, you know. So, oof. Yes, Thursday is an optional review day. So I will just be here for Q&A. Live streaming so that you actually feel compelled to come. I might even do it on WebEx so that you can have video chat. I'm thinking about doing that instead of a live stream. But yeah, that's Thursday. So anyways, programming, since that was a question earlier, so let's get to the programming. So there are programming questions where I either ask you to do some, and I already hinted you at some point, I don't know, maybe on some of the lectures, what one of those questions would be. I was very clear about it. There are questions of what that question is. So if you find that, then you're in luck. If not, then that's okay. If you know the material, you should be fine. Basically, the reason why there's programming in this test is because some of the algorithms are far easier to explain with code than they are with text. So I'll leave it at that much. But there is C++ programming. It's limited to writing functions. They're recursive functions, but they're functions. Some of them are recursive at least, not all of them, I think. But you're basically writing code snippets. So WebEx, yes, it doesn't have lag, but it's super, super low quality. Like, literally impossible to read text. So that's why I'm not a fan of it. But yeah, we'll give it a shot on Thursday probably. Let's see what else I want to say. Review your worksheets. That'll be the big thing. Review my first midterm so you get so remember so you refresh yourself on how I like to ask questions and that kind of thing. Make sure you don't over explain and don't overwrite. You do want to explain your thought process for like the algorithmic stuff, yes, but for the text only questions, you know, keep it tiny. Also, so the type of questions, there is, I think, one multiple choice question, and then there are a bunch of writing questions like essays type where you write stuff only, no pictures, and then there's the file upload ones like the ones you did in the practice ones. The file upload ones, you can include your scratch work along with the file upload. Make sure you clearly indicate the solution. Only one upload per question. Do not upload multiple questions on the same upload. Each one has their own upload to keep things sane for the graders. Furthermore, if any of the text questions you feel like you wanted to have a visual aid for it, the last question of the test is not a question, it's just a file upload option where you can upload any additional documentation you would like to attach with your test, such as any additional visual aids for the text only questions where you couldn't upload an image, or any additional scratch work for those questions, because in the questions with file upload you can include your scratch work as well. But the text only ones, then you can't really do that. So I'll leave that for any sort of issues or last minute things that you need. Anything you feel should be included with the test. Can we do pseudocode, or does the code actually have to work? The code has to actually work, C++. If it was to test in person, I'd be happy with pseudocode. Here, you have a compiler and everything. So I expect you to be able to code these questions and they have to be actually fully running. And you don't need to be doing it on Sally or Bobby in case it goes down. You can do them locally. It's not that kind of level of complication. There are going to be those negative questions from Dr. Dead. Rest in peace. I love those, and we are going to give them a shot. I think they're great because they actually test whether you really know the material versus whether you can Google it. And so we'll find out. I don't expect there to be any sort of curve or anything for this test. In fact, I plan on that not being the case. I have no reason why, because of it being open notes, that you can't do really good on this test. So it should be easy if you know what you're doing. And if you forget like one or two things, you have the internet. What I don't want you to do though So don't want you to just Google the answer and copy and paste. That's plagiarism, first of all. But two, that's cheating technically. I know some of the answers are rather. I even use Geeks for Geeks as a reference for lecturing and also for creating the test potentially, but that doesn't mean you can just copy and paste what they say. It has to be in your own words to make sure that I know what you're talking about. And if in doubt, I will question you on some of your answers live. And if you choke on it, then I guess I'll know. Last thing, logistics is, again, like I said, on Thursday we'll have some sort of additional review Q&A where I can show examples of specific things. And the test does require an access code in addition to being unlocked. That access code will be delivered on a Canvas message and on Discord, but for sure Canvas message because I've already set that. It's time, so it'll email it out at 11:30. You type in that access code, and then you will be able to do the test. Do not discuss the test, as I said, on Discord. Okay, you can discuss it after the test ends, but not during the test. If you have a question, do not post it on Discord, even if it's just a generic question or a typo or anything. Please, I don't want to confuse other people. I don't want you to accidentally give them more information than you should. Direct messages only, email to the TA or me or myself. Once the test closes at midnight, then we can all talk about it, and hopefully it was easy and we're all like, yeah, that was easy peasy, lemon squeezy, or we can all be in tears. So do not cheat, and that means not work with other people. I do have some counterintelligence going in for that, so I will find out. Don't try it. I will do what I must. Okay? So also make sure your internet is good, make sure you're prepared, and most importantly, practice beforehand so you don't get murdered by ABL tree question or heap sort hashing. All right? That is not the code, access code, by the way, because the access code is only true things, not fake things. So, okay, let's see. We got anything on Discord? Nope, no messages on Discord. I have some DMs, but I'll look at those later. So, it's over. We're gonna switch over to office hours. I can review right now, but for those of you that have to do other things, feel free to go. You can watch the remainder left. If you want me to do any examples or anything, I can do them now. Otherwise, like I said, on Thursday, you better come prepared with questions, and I'll also discuss more in detail some of the contents of the test on Thursday. And by the way, Control Tab doesn't do anything. So fake news. Oh wait, that was just that Control Tab. Yeah, see, fake news. But even if I was to click there, you can't see anything. Ha ha ha. It's just the instructions. So yeah. Okay then. So here we got a question. All right. For hash tables, is accessing time O of 1 or is search time O of 1? Because cheat sheet says search is O of 1 but doesn't list anything for access time. Actually, it's not as easy as just saying O of 1 always, because here's the thing. If you're using a hash table, you risk always collisions, right? And you have to have a system set up for that collisions, whether it's open addressing or closed addressing. And so if you had a perfect hash where there was no collisions, then you'd guarantee O of 1. But if not, then you can potentially have access time of O of n for insertion, or sorry, for accessing, like retrieval of the information, which can also be deletion as well. So retrieval and deletion can be up to O of n in separate chaining if you have a linked list. If you have an ABL tree instead of a linked list, then it's log n time. Insertion, however, varies. Insertion, if you have a linked list in separate chaining, it's O of 1 time always, because you can just dump it at the beginning or the end using a tail pointer. You're good to go. However, like I said, accessing time is going to be, or retrieval time is going to be potentially end time. So that's going to be your pro and con between using an AVL tree or using a linked list for your separate chaining, whether you want that O1 insert time or whether you want that log of n access time. Of course, this is only for collisions. Ideally, whether it's an AVL tree or a linked list, is going to be really, really tiny because you have maybe 1 or 2 collisions, but it's mostly quickly accessing. Of course, if you have only one item and there's no collisions, whether it's AVL or a linked list, it would be O of 1 time. With open addressing, it's a whole different story. With open addressing, it can be again O of n time because of all the shifting things happen, whether it's quadratic, linear, double hashing, it's just going to be O of n time, even for insertion. It's just, there's no good things about it other than caching and 219 sort of stuff. Yep, O of 1 for perfect hashing, indeed. So, yep, that's that question. What else? Doggo Padme is sleeping behind me. Oh, she panicked because I stretched. So, more questions? Otherwise, that's the end. Can you do an in-order, post-order, or in-order, pre-order tree? Sure. The only thing with that is that I need a tree to start with. So I guess you'll see the answer before you actually see the tree being drawn. So yeah, I'll go ahead and do that. The pup indeed. Okay. In fact, actually, maybe I don't show you. Let me really fast do a tree and then we'll build it. Yet again, I know the answer ahead of time, but it's okay. So A, B, C, D, E, F. And let me do I guess I'll do in order, post order, since people were saying there was nothing like that. So we'll do in order and post order. So the in order of this is going to be D, B, E, A, C, F. And post order, which is left, right, root, is going to be D, E, B, F, C, A. Okay, I got it done. So now let me go ahead and pop in the lecture. Okay, so here we have an in-order traversal, and as long as I didn't mess up the traversals, we can build a tree from that. So because it's post-order, we know that the last item in the list is going to be our root. I'm just rewriting it nicer. So that has to be our root because that's how post order works. It's left, right, root. In order, on the other hand, the root should be somewhere around the middle of it. If it's like sort of a balanced tree, you know. If it's not, you know, if it's a degenerate tree, and it's like this, I guess it's, well, I draw it because it might be backwards on the video. If it's that way, then it's actually going to be at the beginning. If it's that way, the degenerate tree, then it's actually at the end. But typically what you see is like this, it's somewhere in the middle. But that doesn't matter. We don't need to really know that because the algorithm will take care of that for us. So what you do is as follows. Because it's post order, you're going to start from the end. So you're going to start from the right side and you're going to work your way to the left side. You're going to start there. And so we first identify that to be the root, and then we look for the A in the in-order traversal. And again, this whole thing breaks if you have duplicates, so don't have duplicates. So we have these nodes, and these nodes are represented by what's on the left side and what's on the right side of A. So right now, and this is what I would expect you to write on the test, is you would have this tree, okay? And from there, you go on to the next one. So the next node that we're going to see is a C. So the C is over here. So what that means is that C is the next child or direct child from A on the right side because that's on the right side here. So because of that, we're saying that anything to the left of that will be a child of C and anything to the right of that will be a child of C, but right child. So any nodes here which are none would be left children of C. Anything here, which we do have one, is a right children of C. If we had more than one, it just means that it's maybe a child or grandchild or so on. So what this becomes, and yet again, you would draw this multiple times, would be that, and then nothing there. So you can just put that, or you can just not put a line. Make sure your lines are clear. Please do not do this in the test. Don't do something like this. Because then I'm like, what is that? Left or right child? Like that's ambiguous, right? Like, yeah, no. That's like the whole, there's my true or false letter. So yeah, don't do that. That's ambiguous, okay? So anyways, from there, we can go ahead and look at the next node. The next node that we're looking at is a F. That's F, but yet again, there's no children there, so nothing happens because internally we are looking at this spot here and this spot here, which has nothing on each one. So that's a leaf node. Nothing cool happening there. Next, we're gonna look at the next one, which is B. Where's B at? B's right here. So now we're dealing with this side. So we're saying this is a B. So anything to the left of the B is a left child. Anything to the right of the B is anything to the left of the B is a left child. Anything to the right of B is a right child. So from there, you yet again redraw your tree, set B there, and then set anything to the left and to the right. Because there's nothing but one node, then that's pretty much it. But this could be, if there has like an A here or something, or well, it can't be an A, but some other letter like an X, then that would go here. But I kept the tree pretty simple. So from there, if there was an A here or something like a special character there, X or whatever, if there was something there, first the next thing you would do here is you would go through the E. The E has nothing on the left and nothing on the right, so that just stays there. But then you would get to the D, and then you would see that the X is there and nothing there. So if there was an X here, then it would go over here. But that's just an example. That's not part of our tree, so to not confuse people, let's just get rid of it. But yeah, you're done here because you look at the last thing, and that's how you know you're done. And that is indeed what I had drawn, as you can see right there. That was the one that I did. And as you can see, that looks exactly like what we had. So, yep, we got it right. So, and yes, you do need to show step by step, which means draw the tree like this, this, and this. And if you'd like with the color coding, you could do that. If not, then you can rewrite these things by indicating like how you're looking in left and right. I'll explain that at least for one or two of them for this part, but I do definitely want to see the sort of evolution of your graph this way. That you want to put 100%. You want to put these steps like that. This part here with the color coding you don't need, as long as you indicate for one or two how your mindset is for doing that. So here we have a question. So in order can tell you what is to the left and right of the root, and post order can tell you what you should do, what should be the next root. That is indeed correct. And if you flip this for pre-order and in order, the exact same thing, except you start from here to here. So what is the, let's just do it for the same tree. What's the pre-order traversal of this? Pre-order is root left right, or print left right if you memorize it that way, as I told you to, but I didn't, so I'm stuck with this forever. That's going to be A, B, D, and then from there E, and then C, and then F. So let's just copy your in order. D, B, E, A, C, D, B, what? ACF. I'm gonna do this super fast just to show you, but you start out from this side now, so that's here. So you got A, D, B, E, C, F, and then B, which is there. So that means that's our new root. So you would draw another one, but in this case, I'm just doing it quickly. Then you go to D, but no children. E, no children. Finally, you get to something interesting. You get to C. You get to C. And so C is the next root. So that means that F will go down there. And voila, you're done. As you can see, we built the same tree. So it's the same algorithm. You just start from the other direction. That's it. It's very easy. As long as you know how to do it in one direction, it's very easy to do the other one. It's not an easy algorithm. It's just easy to do the other version. What you cannot do is post and pre, because I can have this pre and this post, which would make the following tree: A, B, C, and then the post of that CBA. That's correct. However, I can also make a tree that has that same system by doing A, B, C. Yep. Both of these trees here have the same pre and post order traversals. These traversals will work for both trees, but they're not, so it's not unique. So this is your counter example that you would have had to put in the assignment when I asked that while you can build for some combination of pre and post trees, if you do build them, there is more than one answer. And so it's not unique. Whereas here, as long as this is a valid combination, it will always give you the same tree. You can never get a different tree from that. And there is no other valid tree. Whereas here, it's the way or the high. Like there's more than one answer. And so it's not really unique. So it's kind of useless for what we want to do with it, which is to build trees uniquely, right? So on the worksheet, were we supposed to do that step by step? On the worksheet, I was a little bit more liberal or lenient on that. But for the test, I will not be. So for the worksheet, the TAs, they're just grading it. And if you got it right, you got it right. But for the test, I want you to show your work. Also, for building a heap, what steps are we supposed to show? Each time you do a rotation, you go ahead and do that. So you got yourself the initial input, which is just an array of level order. Then you got to heapify it, which means the trifor symbol. So that, then that, and then this, which may potentially, if this and this rotates. So like if this one and this one rotated, then you gotta double check this part again, because you might have to then flip, say, this and this. So that's heapify. And so you would have to show each rotation. So there's gonna be a lot of drawing. I recommend if you're doing it digitally, you can copy and paste it. How do you determine if it's in order, post order, or in order, pre-order, if only in order is given? How do you determine if it's in order, post order? So if in the test, I will tell you like which traversals you're getting. But if you didn't know, if somebody told you like, yeah, that might be the pre-order or the post order, we talked about this, I believe. So one of the things that you can do is you can just try it, and then once you build the tree, you can perform the traversals on it and see if you get the same traversals, and then that's one way to know. Frankly, that's the best way to do it, to be honest. Other than that, you can look at what the root is, but that's not really going to tell you much if it was like a degenerate tree or something. So really, it's what will build a tree out of it, and what will build a unique tree as well. You may get invalid data as well. But in the test, I will 100% tell you which traversals they are. Did I miss any questions? If I did, just repost them. Let's see, nobody asked anything on Discord. I know you guys were panicking about where it was, but sorry, I think we started like 2 minutes late. There's no way I can speed up the timer either. Is it considered accessing or searching with a key in a hash table? Technically the same thing. Accessing. Well, searching is an iffy word. With hashing, you don't necessarily search, you access. It's not sorted data. So searching is kind of an ambiguous word, but typically they mean the same thing. Because it's accessing an index where you're searching with a key. Yeah, I suppose. Can you explain that unique tree thing again? Yes. So with an in-order traversal, if you have this combination, if you have in and pre or in and post, you're guaranteed that they are going to make a unique tree. And by that I'm saying when the tree comes out from the algorithm and you run the traversals and you see that you're getting the right traversals back. So that's a good way to test. When you finish doing your tree, go ahead and print out the pre, in order, and post order traversal and compare them to the original input. They should be the same. That's your most important way to figure out if you messed up. That's because it's always a unique tree. There's only one answer per se. That's what I consider unique. Pre and post combination does not make, assuming they're valid pre and post combinations, like if I just took the pre-order and post-order of this tree that we've made, and I try to make a tree out of that, you can see that I can make more than one tree that have the same pre and post-order traversal. And the easiest way to do that, I could try to show it to you, although it might be tricky. It may or may not be the case, actually, although I think it will most likely be the case. So that's the pre, right? How can I know? Well, I know the A is the root, so there's that. Technically, that's the post, because this is the pre. Yeah, so. So that's post, and that's pre. So one tree that I could make, of course, is the one that I made already. But if the other trees that I could make potentially from this, that would be valid, would be, I don't even want to think. I could take the tree that I have right now. And I could fiddle with the leaf nodes F. If I switch this guy here, so I switch it from left to right child, I should still get the same traversal. Yeah, because post order, once we do E, did I copy the right post order? So post order, yeah, okay, so D, E, B, and A, and then from there you go to F, C, A. So the post order is valid, and for the pre-order, we got A, B, D, E, C, and F. Yep. So there you go. I have now shown you an example. And there might be an algorithm to show at least one example of a combination that's valid. You could probably develop that. But off the top of my head, can't really think of that. You definitely don't use the same algorithm that you do for the other ones. So here's an example of two different trees that have the same traversals that we had. Of course, this is the one that we started with, but if we were just given the pre, post, and pre, we could end up with the left one too. And they both create these traversals. So we would say that you cannot make a unique tree, so there is more than one answer. So if in the test I said build a tree from these two traversals, I could get any of these answers and they're both technically correct. In fact, I bet you I could get maybe a couple of more, but at least this is the easy one that I can think of. The other ones I have to really sit down and figure out if they even exist. Is an ABL tree a full, complete, or perfect tree? So that's a good question, because it doesn't have to be a complete tree and it doesn't have to be a perfect tree. And a full tree is one that has either 0 or 2 nodes, and ABL trees can very well have one child. So because of that, an ABL tree does not have to be full, complete, or perfect even. So to be balanced. So you could have a balanced tree that is none. So if you would like a counterexample of each one, this of course is a complete tree, but now it's not. But it's still a balanced tree, right? We can check the balancing. So here we have not complete. Of course, this is not perfect either. And so full is the only one that remains. So full means 0 or 2 children. So we either have leaf nodes or we have nodes with 2 kids. And yet again, that has one kid. So breaks the full property as well. So balanced trees can be none of those and still be balanced. But you can have balanced trees that are full, complete, or perfect. However, not all balanced trees are full, complete, perfect. So maybe I should write that down. So I'll just abbreviate. So while you may have balanced trees that are full, I guess I'm not abbreviating, complete and or perfect, while you may have, there are also balanced trees that are not full, complete, or perfect. I think I said it better than how I wrote it. I just rewatched the audio. So it has a math thing. It's like a relation. You know, it's like a unidirectional relation. Math people can probably tell you how the proper terminology of that is. So that's as much as you can know. And yes, you can also have a full tree that is not balanced, by the way. So you could also have this tree is not balanced. However, it is considered a full tree. So it fails that property. As for complete and perfect, yes, all complete and perfect trees will be considered balanced. Yeah, because complete trees have that one level difference, so it should be okay. And perfect trees, of course, are always balanced because they're full, so that's great. Are there going to be questions on the test to build a tree from pre-order and post-order on the test if they can produce different correct trees? Maybe. I don't know. I can't tell you that without telling you if the answer is yes or no. So you should definitely be prepared for the possibility of having a question that asks you to build trees from different traversals, including in order, pre-order, post-order, and level order traversals. That's the approved answer from the high command. Other questions? How many people have we still got live? I think I saw a thing that I can control my stream from Twitch, from the Twitch TV app. So maybe I should have done that. Because here's the thing about that: I can set this to data only, and then I can watch the stream using data, and it shouldn't mess with my internet. Yeah, I forgot I could do that. I was gonna test that today, so I'll probably do that next time. Oh, nice! I got a bunch of people following me. Oh, I can even chat here? Let me see. Say something. Hi. Yeah, it works. At least the chat works. Yeah, perfect. So I have 34 viewers. Oh, wait, no, 9 viewers, 34 followers. So yeah, and we're just about to hit the 2-hour mark too. So, any more questions, or shall we call it? So, for those of you that are watching on the recording later, or for those of you that are still here, on Thursday it's optional. It's strictly review. You don't have to watch it. You don't have to come. We may do WebEx. We may do Twitch. I think WebEx might be cooler because I could see you, even though it'll be really bad quality, but that's okay. Come prepared with questions. You can ask me like, hey, do like right now, do an example of an ABL tree, do an example of building a tree from that. That's fine. But you can also come prepared with specific things that you might want me to refresh on, or that you may want to question more. I'll talk more about the test. I should hopefully have back the results from the TAs. I will post them as soon as I get them from Discord, of how long it took them to take the test. If I see that the TAs finish it in like half an hour, that's when we'll have to cut down the time or something, because then I'll be like, okay, that's excessive. But I expect them to finish in about an hour, so we'll see. You never used WebEx before. You do not need to make an account to use WebEx. If I do use WebEx, you'll get a link. You click on that link, it'll lead you to a download page. You will install some spyware in your computer, basically. That will then automatically run everything, and all you gotta do, it'll ask you to put like a username and an email, but these can be basically garbage because it's not a real account and it doesn't have like an email checking system or whatever. And then you basically connect to the video, and when you're done, and that's why it's very open to hacking, because anybody who has the meeting code can join, and the meeting code is part of the URL. So don't share the URL with people that are not in the class, otherwise you get people that are jumping in there. I can make it more secure where I have to grant access to each person individually, but that's of course once we have issues with people coming that shouldn't come and things like that. But we don't have to use WebEx. I'll figure it out. We'll see. It might be a good test run just to kind of get a feel for WebEx, but it does require you installing software, which is always a pain. Do we have to have a webcam? Well, you don't have to, but I'm just saying in WebEx you have that opportunity to not just speak to me, but I can see you potentially if you want. Yeah. Otherwise, text questions work too. I haven't been joining Discord during the lecture because I'm scared that anything that takes bandwidth away from the lecture is bad. But I can try to do it on Thursday as well if we do Twitch, so you can still ask questions by voice. So, yeah. Anything else though? I'll post the logistics of that. I'll keep updated on Canvas and Discord. All right. It seems like we have no more questions. So then I will go ahead and end the lecture, and then we shall reconvene on Thursday. But regardless of that, remember, your test is on Thursday, or Friday, I mean. So here, I'll put it here actually. Reminder. Test is this Friday at 12 p.m. Technically 11:59. And you will need an access code, which will be posted on Canvas announcements half an hour before. It's pre-programmed. I will also, if I'm alive at that time, I will post it on Discord as well. Do not share that code with anybody not in the class, although they shouldn't be able to take the test in the first place. But I'm doing that mostly so there are some people in the class that can't take the test, and so yeah, I don't want them to access the test, basically, for academic integrity purposes. Also, like people that drop the class that may not want to deal with the test or whatever. Okay, all right then, nothing else, so that's it. I shall end it. I hope you guys have a good day. Study, ask me questions. You have no homework from 302 right now, so you should be using this time to practice. I think the most important thing you can do for this test is not memorize things, because it's open notes. You can have a cheat sheet or whatever. What you need to do is you need to make sure you can do these algorithms efficiently and quickly and correctly. Building the tree, that kind of stuff. It's not enough to just know how it works, but you need to practice it. Do a couple of them. How do you come up with examples? Build a tree first. Do the traversals. Go play some video games. Come back 3 hours later after you forgot what the tree looks like, and just look at the traversals and build the tree back again. That way you don't have the solution. Build a tree from the examples that I gave you in the assignment 6 or 7. By now you've forgotten what the answer is. Just take the PDF and build a tree from that. And with ABLs, it's much easier. Just pick random numbers and just keep inserting it and make a massive tree. So that's what's really going to help you in the test. Is not just knowing how these things work. Most people know how they work already. What they're not comfortable with is actually doing it on the spot quickly without getting stuck. Especially historically. ABL trees has been the hardest question in the entire semester in test. Maybe second only or tied with the recurrence relation stuff. I don't want to see those statistics this time. You need to practice ABL trees. If there's one thing I would say you need to practice, like one more problem of, is ABL trees. We can do more on Thursday, but practice them. Because ABL trees, you think you got it, but then you got some nasty rotation and you just get stuck. And I don't want that to happen. So you just practice makes perfect in this case. And I know you guys will do good if you practice. Because you just open notes. There's nothing you got to really memorize. It's all about just getting these things working. Yes, we can definitely do an example of deletion. We can do a big example with a lot of inserts and a lot of deletes of ABLs on Thursday indeed. All right? Okay then. Well, I know you guys got to go to your classes and things. And those who are watching on YouTube, if you watch before Thursday, be there on Thursday, high noon. I'll see you then. Thanks for watching. Have a good day, guys.